Perfect.
So Leonardo will talk about the joys and tribulations in building a transformational observatory, ALMA.
Okay, so obviously I will not go through the entire history and I will not go through the entire set of details. I hope I will give you some of the, some nice thoughts about what we went through in doing what we are doing, because I think it's also useful for the future. So first of all, if I can get, okay, and Zoom has too many windows for me, but I'm making, so how do you, in a nutshell, how do you, the answer to how you get to an observatory like ALMA is that you need to have a vision, you need to work hard, and you need to have a lot of determination to be able to achieve this. So vision, let me see if I can get rid of this. I have the Zoom things right on top. Okay, I forget. I hope you don't have it. So one important thing when you want to build something like ALMA, you need to have exceptional science goals, because you really want to make sure that you have a huge impact in the fields that you are targeting. And that's a key role. You have a vision, you have to have a vision of where science needs to be on a 20-year timescale, because this is the timescale that it takes to set up, at least the timescale to set up something like this. And I'll tell you more in a minute where ALMA came from. You have to deploy something that you don't have at the time you are designing the instrument. So, really ALMA, when ALMA was conceived, nothing of what you see on ALMA today was achievable, okay? Very little was achievable technologically. And you have to plan on having a huge expansion of the observable space in terms of the parameters of your observation. In the case of ALMA, as you will see, we focused on three aspects mainly. One was wavelength coverage, trying to cover a broad range of wavelengths that was only minimally explored at the time of conceiving ALMA. We tried to go to a factor of 100 better sensitivity of what was available, which again is an enormous factor, okay? And a factor of 10 to 100 also in the angular resolution, which is the other huge improvement, okay? So vision, the first thing, you need to think of what will be needed in 20 years, 20, 30 years from now, not what you need today, which is a bit challenging, but that's the way you have to think. You have to have heart, you have to work hard, because you have to, typically if you want to build something like this, you have to find money and manpower to do it. And to do this, the only way is there is no magical recipe. Nobody has, the millions in his pocket. You have to inspire the community. You have to convince the skeptics that you can do this, and you have to hire the best and diverse people to do the work. So, and this is important, best and diverse people. ALMA is not a rooftop observatory, okay? It's not your amateurish telescope where you and 2 other grad students can do everything from the engineering to the software and do something. You need to realize that when you are leading into ALMA, you need to realize that there are things that you don't know and you have to hire people that know those things. So I like to quote always this from MAYA, this Apologies of Socrates sentence where it says, I'm smarter than you because I know that I don't know the things that you know. Okay, so it's important for people leading an observatory to realize where they need help because they cannot do it themselves. And this, sometimes is missing more than you may think, actually. And finally, determination, because no matter the vision, no matter the hard work, at some point there will be difficulties. At some points there will be things that don't go to plan, and you have to maintain optimism, focus, and you have to always aim high and always keep aiming high. As I always say, but this is true of everything in science and life in general, if you aim for if you want to achieve 5, you have to aim for 10. If you aim for 5, then your best, you're going to get 2 or 3. So that's a very important thing. You always have to push the limits. Okay, so these are the three things, and I are the three things that I put at the beginning, and they will come a little bit through the things that I have that I'll be saying. But I think is an important perspective that you have to have when thinking about ALMA, but in general, when you think of a big project in science. So when did ALMA started? So a friend sent me a book a few years ago, The Conquest of the Moon, which was written in 1889, which was describing an observatory on the moon. And if you read on the caption there are 25 exactly like this one. And so at that time, he was, you know, pulling my leg a little bit on the fact that we in Europe, we were doing 25 identical antennas for ALMA. And this, he was wondering whether we were got inspiration from the past. But obviously, no, this is a joke. ALMA actually was born not as ALMA at that time, but was born actually in the 80s, incredibly, as you might think, in the mid 80s, when we were about to, we did not even had this image, but we were about to get this image of from the existing millimeter arrays. Okay, millimeter arrays in the 80s were in the first early days. Okay, there were 3-4 antennas expanding to 6 type of arrays. There were two small observatories in North America, in the US, the Berkeley, Illinois, Maryland array near in Northern California, and Owens Valley Radio Observatory in Southern California, the usual dichotomy between North and South California at that time. The Nobeyama Radio Observatory millimeter array in Japan, and the Plateau de Buer interferometer in Europe at IRAM, okay? And basically they were the only millimeter interferometers existing at the time. And they were starting to discovering things. This thing here on the top, I don't know whether you see my cursor, but in the top left is essentially the first image at millimeter wavelengths of HL Tauri in the continuum and in the gas. And at that time, there was a huge debate whether this was, well, everybody was aware it was a young star at least, but there was a big debate whether this was, what we were seeing was a disk, was an outflow, was infall from the cloud. It was very uncertain what it was at that time. And I show this because it's at this time, then people started to have a vision of what they wanted as a next step. Okay, they realized that these arrays were going to do great science, and in fact, they continued to do great science throughout the 90s and the 2000s, but it was not possible to actually do the next big step as part of these small observatories, university observatories, or small collaborations, like in the case of IRAM, okay, within Europe. And it was necessary to think big, to think of a new, completely new approach. And in the early 90s, basically ALMA was gestating as a global partnership. What you see here are the three things that are on the left side were the three ideas that were floating in the mind of Europeans. The large sub-millimeter array. Europeans were aiming for large antennas and a huge collective area with a limited number of antennas. That was their goal, essentially an extension of the initial things that they have been doing with the Plateau de Buer. The millimeter array in the US, which was essentially an extension of their ideas of having many small dishes. Okay, you have, and then in Japan there was the large millimeter array. Was the idea. Eventually, something very good happened, which only rarely happens, unfortunately. But the millimeter and submillimeter community of astronomers realized that they were still a relatively small community at that time, and there was no hope to basically convince one of the individual poles, North America or Japan or Europe, to actually build a huge observatory that would meet the specification, they had to get together and perhaps build something even bigger that they had in mind in order to achieve this. And so that's how ALMA started. Okay, ALMA started as a collaboration, first of the European and American project, but with the Japanese, that was the East Asia that was already planning to join. And this is actually the original memorandum, where resolution is called, between ESO and an NRAO, signed by the Director General of the two organizations in June 1997, which aimed at build a common project in the northern Chile. You see here, no? Organize a partnership that will explore the union of LSA, which was the European one, and MMA, which was the American one, into a single common project to be located in Chile. Why in Chile at that time? In Chile, because they all realized that the sites that they had been using were not ideal. And we needed a site for millimeter astronomy that was dry and was in a location that would allow long baselines. And the only option really that was explorable was the Chilean Andes, where already Europe and North America had other observatories, okay? So this was in 97. There was a lot of back and forth, whether you want large antennas or small antennas. Eventually they sit exactly in the middle of what the two projects wanted originally, 12-meter antennas. And finally in 2003, the trilateral project started when Japan joined, bringing important contributions, essentially the ACA and three additional bands. And then other partners joined, Taiwan, South Korea, and others are other countries, for example, joined Europe and joined ESO, sorry, and so on. Okay, and NRAO was already from the beginning already had an agreement with Canada, with the National Research Council of Canada, for the participation in this ALMA project. Okay, so eventually, altogether, this was the design of ALMA. Okay, this is what we set out to build circa 2001. Okay, this was, or 2003 if you want. At least 50 antennas of 12-meter diameter. The at least is important, as you will see in a minute. Frequency range between 30 gigahertz and 1 terahertz, 16-kilometer baselines, compact array. And all the vision was shaped around something that may look simple, but at that time were three by far not achievable science goals. Okay, by far not achievable with the current instrumentation. The first, the detection and mapping of molecular and atomic gas in a normal galaxy, quote, up to Z3, okay? So this basically, this science goal was driving the sensitivity and the frequency coverage of ALMA. And then the ability to map dust and emission and gas kinematics in protoplanetary disk to study planet formation. This was very far from what was achievable, as you have seen from the postage stamp that I showed before of HL Tau. And finally, provide high fidelity imaging at sub-millimeter wavelengths at 0.1 arc-second resolution. So the idea was to provide high fidelity images at the same resolution as the HST, essentially. Okay, so this also was extremely difficult because, as you know, ALMA is an interferometry. So high fidelity is an oxymoron when you talk about interferometry. And 0.1 arc-second resolution was a factor 10 almost with what was achievable at that time in terms of angular resolution. Okay, so these were the science goals. This is how the site looked like with the ALMA Science Advisory Committee in 2001. At that time, it's also interesting to have a look at what they were thinking in giving their advice to the ALMA project at that time. So at that time, in 2001, there was the discussion of where to put the array. So Chanantor was prepared finally as the ALMA site. They set the calibration goals that we are struggling still to achieve. We have not yet achieved 1% at millimeter wavelengths and 3% at sub-millimeter wavelengths. That's not trivial at all. And then at that time, we were already thinking of upgrades by the baseline correlator that was proposed at that time. Okay, what now you are using as ALMA users is not the original baseline correlator, is an upgraded version of the original correlator that was discussed at those times. Okay, and there are a few things on the science concepts that are interesting, but I don't want to spend too much time. Then what happens in the mid-2000s when you start to go on the ground? This is what the great plans, no? Having the observation support facility at 3,000 meters, just below the threshold for Chilean labor, so that you don't have special problems. Then at 5,000 meters, you have the big plateau with all the antenna stations. And the correlator would be up there, and then there would be a connection with the fiber cable for the power going up, and the data going down to OSF, where the archive would reside and all the operators would reside. Okay, so all look fine. Let's start working. And when you start working, you start receiving the first builds, and then when you met reality. But even before the builds, the first reality that we met was this one. Early on, in any observatory construction project, you have to find the rodent and take care of the rodent, because there is always coming to be one. You are all too young to know the LBT story. There was the red squirrels. At ALMA, we had these nice little ones, which are sort of 20-30 centimeter mix between a rabbit and a mouse. And one of the big things was to try to identify where they were living, because we had to avoid their colonies with the foundations and the road, obviously. The problem, obviously, is like any good rodent, these ones were basically hiding for all day and coming out only at night, which is very hard to do, to look at the site. So at that time, the staff of the observatory was very limited, and there are rumors that the director of ALMA at that time was actually going around the site trying to find out the colonies of these things by looking for their poo, obviously, because it was the only thing remaining on the ground. This is how the environmental impact was done for ALMA in early 2000. We had directors that were really going into the field and do some real work at that time. And here you have also another interesting thing, the gas pipeline. One of the nice things that we thought it was possible at that time was to use gas to basically produce electricity. And we were thinking to attach to this gas pipeline. And obviously, being astronomers, we knew nothing about all about energy production and so on. So just to make a story short, eventually this gas pipeline, we are not using it, because first there was gas going in one direction, then there was no gas, then gas going in the other direction, then again, no gas at the time being. So eventually we are producing our electricity from OSF by shipping gas to OSF, just to tell you the things. But this is to show you also some of the practical things that appeared at the time when you put your dreams into reality. And one of the big one of the big scary things that we had in 2005 as young astronomers at that time, I picture you as myself at that time, more or less. And we were all involved in ALMA. In some sense, we were dreaming of ALMA, using the existing millimeter array and dreaming of ALMA. And we were involved, for example, in the ALMA Science Advisory Committee at that time. And we got this somewhat scary charge to basically advise the ALMA management and the board on what to cut, because the money was not enough. And so we spent 1 year in desperation trying to find the things that we could live with in some sense. And here is an important lesson, where to draw the line when you do this exercise. So the thing that we decided to focus at that time was to make sure that ALMA would maintain the ability to achieve the 11.1 science goals. Okay, so the science vision was paramount. And we supported, in some sense, the ferring rather than designing out capabilities. And also focusing on the ferring things that could easily be upgraded be implemented as upgrades of ALMA. Okay, trying to cut or block the what the people like us, like me at that time, were actually thinking. So people that were more focused, if you want, on the budget and construction rather than being focused on science and what do you want in 20 years. So that's why your role is important, because you have to focus on this. And the obvious easy things to cut were number of antennas. Antennas were very expensive. And after all, at that time, ALMA was 64 12-meter antennas, while the existing arrays were 10 antennas. So people were saying, well, if we go with half of that, you are still good enough, no? You are still better than existing. But obviously adding antennas later on would have proven almost impossible. So this was one of our red lines. The other red lines was the paths and baselines, because we knew that developing the site was hard, and the signal chain capability. So here I recovered some of my slide from that time. And here you see I tried for these stupid automatons like myself now, some simple way of telling them what not to touch with this green, red, and yellow thing. And one of the scary things that you see here is that one of the things that was seriously considered at that time was to construct only baselines up to 4 kilometers and not beyond, okay? And another thing that was seriously considered was to basically do only one IF instead of 2 IFs, okay? So no polarization, half bandwidth, and so on. These were seriously considered, okay? So when you are asked about this kind of things, don't assume that senior people know better than you, okay? So eventually we managed. And then there are the joys of construction. And we go fast on this. So this picture, we set together with 3 very different cultures, each with its own plus and minuses. Since I'm European, I will focus on the minuses of the Europeans, because that's what I like to do. So Europeans were always late, of course, in this project, in providing stuff, up to a point that our test antenna, instead of shipping via boat to the US, we had to ship it with a supercargo. So here you see the half of the European test antenna being shipped as a single piece with this huge Lufthansa cargo. Okay, then we evaluated, as any good project, we evaluated 3 antennas with the idea of choosing one. And obviously each of us kept his own antenna. So the Europeans build the European antennas. The North Americans build the North American antenna, and the East Asians build the East Asian antenna, which actually is a good thing in the end, but this I leave for the question. And then we had, some interesting way. This is the first antenna that was going through Antofagasta to reach the observatory in 2007. And then we were assembling the antennas at the OSF. And the Europeans, being late as usual, they were working even at night to recover time. Another important thing that I wanted to show is that even in a project like ALMA, where you have a lot of high technology, there is also a part that is not so high technology and testing. Here you have the testing of the water vapor radiometers with their own nice radiation shield in pure cardboard. And the radiometers are here. There is the hole here. And when they look in the same direction, they see the water variation in the atmosphere. One is red and the other is blue. When you insert high-tech tilting devices for astronomers, the coffee cups here, then you see that they look at 2 different patches in the sky, and you see that the short variations in the water content are different, but the long variations are common because they are lower in the atmosphere here. And the water vapor radiometers are actually one of the key features of the ALMA telescope that allows is the sensitivity that we get now. Okay, very quickly, we had other interesting events that I'm happy to discuss when in the questions, like eruptions by nearby volcanoes, torrential rains in the driest place on Earth. But eventually, we managed to build the telescope that you have all seen all together. I mean, this was a great achievement by all the three regions and the associated partners together. Okay, what you have here is again the image of HL Tau at the beginning of the ALMA dream, then the image of HL Tau with the best array just before ALMA, okay, and the image, the famous image of HL Tau with ALMA, okay. All this is possible because of what I said, because of the resilience, the determination, and the hard work and the vision that the people that built ALMA had. And now, where are now? And I'll finish with this. Now we are at the moment in which we are trying to implement a new vision, the next step for ALMA, the future. And we have three main science goals for this. Again, one on the origins of planets, one on the origin of chemical complexity, and one of the origin of galaxies. So pushing from right to left, angular resolution and sensitivity, spectral capability, so spectral survey capability, and again, sensitivity for the origin of galaxies, okay? So we are aiming to build a telescope that is a factor of 10 faster than ALMA in spectral survey speed, at least a factor of 2 more sensitive in continuum sensitivity, and at least a factor of 2 in improved angular resolution. And this is a moment where we need you, because again, people like us will start to say, we start to tremble, we start to think that, or maybe is too large of a jump, or maybe it costs too much, or maybe it's too difficult. And that's the moment where you have to step in and to push for the science and for achieving what you want. Okay, and I'll stop here because it's already too late. Sorry for this.
Well, thank you very much for this overview. All these fantastic anecdotes. I mean, we all very enjoyed, and also your engaged talks. Very nice. So we have questions, of course.
Yeah, thank you, Leonardo. That was very interesting, especially seeing these old photos. That's really cool. Violetta actually has a question about this. So in the picture that you showed of the prototypes, they look slightly different from the final antennas, but were they still adapted afterwards?
Yes. The short answer is yes. So these all three actually were adapted, some more than others. In particular, the European one was changed very, very significantly. So the European one is the one on the right side, and the two main things that are difficult are the support of the secondary, obviously, which is completely different, and the interface actually with the foundation, which was a 6-leg interface, and now we have a 3-leg interface. Yeah.
And I think Ivor was picking up on your, suggested question already. So what's good about these being 3 different types of antennas?
Well, that we pushed each other very much on this. So we all said our antenna is the best and will work fantastically. And so at some point, since we then went each our own separate way, we were forced to make sure that this was true. So this was one thing. Otherwise, otherwise would have been easy to cut some corners with some of the antennas. Yeah, and there are antennas that perform better for in terms of their what is called dynamical performances, in terms for single dish measurements, and antennas that perform better for other purposes. And also they have different systematics for polarization, which is an headache, but also an opportunity to check what you are doing.
Nice. There's one last question. What's the consideration that we finally adopted the spiral-like antenna layout?
UV coverage, instantaneous UV coverage. Sorry, yes, I didn't went into this, but that's basically the best compromise that allows you to have a good combination of small and short and long baselines and uniform coverage for snapshot sensitivity. That's why, I mean, we do a lot of surveys with very few minutes of integration time, and the image comes nice. That's because the UV coverage, the instantaneous UV coverage is fantastic. This is not true in the long baselines. Huh? The long baselines, we have the Y configuration because of the topology of the site mainly. Let's see if I can show you this very quickly. So the spiral is really in the inner, in this inner part. Then when you go to the long baselines, you have this Y-shaped configuration. And so there you need to have a slightly longer Earth rotation synthesis. But on the other hand, since long baselines, you normally need much more sensitivity. This is also fine. You have longer integrations.
I cannot resist to ask a quick question. Is how do you see the future of ALMA? Will it be small upgrades or one big upgrade maybe later? Or
what we are aiming now is this. So what we are aiming is an upgrade of all the receivers, of the correlator, the archive system, and the signal chain. And we are aiming to have 4 times the bandwidth as we have now, and also to have spectral resolution that is high spectral resolution in the full bandwidth. This also has to come with the rethink of the software, obviously, because I don't think that you can just plan on using what we are using now to calibrate an imaging, what we will deliver. But this we are already implementing, okay? This we are trying to implement now, all this lift up. The second, and we hope to have it done by the end of this decade. The second step will be longer baselines, factor of 1.5, 2. And then we'll see. Then it depends whether we find people engaged with ALMA. We need people that bring a vision and rally the community.
Okay, so with this, thank you very much for this overview. It was very, very nice to listen to all this.